I'd like to actually talk to you guys, though, about the importance of Euler's identity and how that is very important when, say, we want to plot the magnitude and phase of an amplitude spectrum. Okay? So let's just draw Euler's identity right now. Okay? I'm taking this right out of the blue book. So that's plus or minus I sine x. Okay? Now, I don't expect you to get to this next step from there. If you can, great. If not, it's right in the blue book, and we're allowed to add the blue book. So these two equations are extremely, extremely important. Okay? And they're in the blue book. This is all on page 29. You guys should really fall in love with page 29 of the blue book. Okay? I'm talking about you just want to take that page, rip it out, and make blood. Okay. All right. Why is this important? And I'm actually going to rewrite this a bit just so I think it's easier to manipulate when you have it in this form. Okay, why is this important? Well, because from taking this, you can actually figure out what your amplitude density, excuse me, not amplitude density, what your amplitude spectrum is, okay? And you can get the magnitude and the phase. So, and remember, what we discussed in a previous video was that the Fourier transform is linear, right? But even more importantly, just say I wanted to add these two terms, I would literally just be adding these components, right? Or if it was just one of these, it would just be these two components. So let's just say hypothetically that I had cosine, and again, I'll say omega 1x plus sine omega 2x, right? When I added them together, I would get these, if you will, four terms added together, right? So that's 1/2 e to the I omega 1x plus 1/2 e to the negative I omega 1x. I'm going to write down here, minus 1/2 I e to the I omega 2x, right? Plus 1/2 I e to the negative I omega 2x. Okay? So, you guys are probably wondering, what does this mean? Well, this actually has a lot of implications. Okay? I'm going to go ahead and erase these three identities since I've already used them for what I need to do. Okay. So let's go ahead and actually plot now our magnitude. So what is our magnitude for our amplitude spectrum? Well, it's just Fn. Key thing Fn. Not, I can't emphasize this enough, these are not equal. And we already did this in the last video. We showed what this is. They may actually look very similar, and in fact they look very similar for periodic functions like sine and cosine, but they're not equal. Okay, so Fn, and then as a function, and then on this it's just omega. Okay? So, what do we have here? Well, we know for all of them it's going to be a magnitude of 1/2, because that's what E is being multiplied by, like your exponential, that's what it's being multiplied by, the real part of it, okay? So let's just go ahead, and since it's magnitude, it has to be in positive, okay? So what do we have here? Our first two are at omega 1, and let's just say omega 1's closest, or let's just say omega 1 absolute value is less than omega 2. So it's going to be closer to the axis, okay? So omega 1, negative omega 1, we know that the magnitude is 1/2. Boom, boom, okay? Omega 2, so omega 2, negative omega 2. Again, amplitude is 1/2. Simple enough, right? All right, good. Now, let's get into our phase. Okay? So, what we're looking at here is, again, let's just same location, but they're going to have a phase. Because it's periodic, it's going to have a reflection. It's going to also be line spectrum, the phase. Okay? And again, this is for the amplitude. Well, actually, both of them are. Well, let's not go down that rabbit hole. Let's just do it. Okay. So, what is it going to be? Well, for omega 1, there's no I. There's no imaginary component in your f of n, right? So it's just 0. Now, omega 2, as it turns out, we do have the I, right? And as you guys may know, I think it's an identity on page 29. It is. Okay. Pay very close attention to the unit phasor. That's very important. But one thing I'll just draw right now is write is I is equal to exponential I pi over 2. And that's just literally to show you how it goes around the phase angle when you have an imaginary component. Okay? So taking that, we know that because it's only imaginary component, it's not complex, it has to either be pi over 2 or negative pi over 2. So looking at it, we know that it actually does that.